Today we present optimizing monkeypox lesion segmentation via kernel density estimation techniques. Monkeypox is escalating health concern caused by monkeypox virus, which is DNA virus. Its transmissions through the direct contact with the infected individuals, animals, or contaminated objects. The illness typically has incubation period from 7 to 14 days and present clinically with the fever, headache, fatigue, myalgia, and continuous lesions. Continuous lesions. Diagnosing monkeypox slowly through the clinical presentation remain challenges because many diseases produce similar scale rashes, especially when lesions exhibit atypical dermatological characteristics. Therefore, monkeypox image segmentation is a critical task in medical imaging and dermatology. The accurate lesions identification support diagnosis and lesions classifications and treatment planning. The research problem lies in the difficulty of accurately segment monkeypox lesions from just medical image. This is not a straightforward task because lesions appearance varies from one patient to another, depend on skin pigmentation, illuminations and conditions, image quality, and the stage of lesions development. Monkeypox lesions may also differ in size, shapes, color, texture. That all make single probability density function models insufficient to present all lesions pattern accurately. Here the challenges become greater when the pixel intensity value of lesions overlap with those of healthy skin. Uh, Scales or other skin inflammations. Additionally, similar dermatological conditions such as chickenpox or eczema may also show virtual distribution close to uh, vi- visual distribution close to monkeypox lesions. This leading to segmentation and classification error. Therefore, using global thresholds may is not suitable for all images, especially when illuminations is non-uniform or when different region of the image has distinct local features. To address these challenges, the proposed study introduced lightweight statistical approach that doesn't rely only in deep learning. Uh, the, that doesn't rely on deep learning. The method is based on probability density functions and local threshold. Instead of applying one fixed threshold to the entire image, here in our approaches estimate pixel characteristics within local image regions. The bandwidth parameters, here we mention H, plays important role in controlling kerning estimation. This help improve separation between the lesions and background of image. As a result, the proposed method provide practicals and computationally efficient alternative to deep learning model like UNet or Deep Lab V30 plus 3 plus, especially in resource limit when have resource limited in clinical environment. The proposed methodology contribution fair statistically segmentation suited for resource limitation setting without deeper learning. Probability distribution uh, the fiction's best segmentation model for monkeypox lesions. Using lightweight alternative to UNet or any others deep learning method. Locally adapting threshold into a cooperated gradient and sub-image area and bandwidth coefficients balancing Pi's variance rate of in-kernel estimation. The steps of models. First, we use datasets. Here, the study used monkey section lesion dataset from Kaggle. It contains 228 sample splitting from 102 and 2 monkeypox image and 126 is not monkeypox image. Is different disease like chickenpox or eczema or others. The non-monkeypox class includes similar skin condition. Here, which makes segmentation challenges. In pre-processing steps, the RGB colors image are converted to grayscale. Here we use the grayscale to reduce complexity. Then we apply medium filtering to remove the noise from image. Then we use CLAH to improve local contrast, so the lesion's boundary become easier to detect before segmentation. In next step, we apply kernel density functions. This method estimates the probability density of pixel intensities using kernel function. The bandwidth parameters H here play central roles because it controls the smoothness of density estimate. Where HB is small, this preserves fine lesions details but may increase sensitivity to noise. Otherwise, with larger edge produce a smoother estimate but may obscure small lesions boundary. After KDE estimate, local threshold is applied. Instead of using one fixed threshold for entire image, global threshold, here the threshold value is adapted within the local image region based on a gray levels value and neighborhood properties of each pixel, such as mean intensity and contrast. This improves lesions background separation and the variable illumination, and skin pigmentation lesions appearance. Finally, the segmentation performance is evaluating use many metrics such as AMS to measure pixel level error and Jacquard to measure the overlap between the segmentation lesions and the mask and the ground truth mask. Here we have to mention the challenges of here to optimize the kernel functions. The proposed study introduced lightweight statistical approach for lesion segmentation without learning deep learning. We mentioned this area. How the method based on probability density function, we say, and also threshold, where the threshold value is estimated with the local image region, the function. This allows the method adapts variation emulation scalar lesions appearance. In this way method, in this study we use uh, 5 kernel functions. Defense is uniform, we as shown in the tables. The results yielded that the Gaussian functions and unifier was the best kernel functions, and the Gaussian is the high performance than others. We can see that mean square error is on Gaussian produce or 50s, and PCR was 23, and we can see thus the Matisse measurement. The record in Gaussian was from 0.92 to 0.95. This is can be say that a kernel was the best structures and preserve this mean preserve structure and minimize the noisy and produce smoothing intensity transmission lesions. To compare the proposed kernel with the deep learning, we also show in these tables. We can see the difference of from the results from our kernels and deep learning function or method. Still, the award proposed are best performance. So the performance here we can say the performance of Gaussian and uniform is much better than others, and it is not a coincidental. This because is the this method has the ability to accurately capture the distribution of pixel intensity in scale lesions. Uh, Also, the smooth bill shapes are weighting function of Gaussian kernel, which is effectively preserve structure and reduce noise. This explains why the margin of lesion exhibits smooth shift in intensity. Consequently, this accounts for the elevated lag the SSIM 0.99 and Jacob was 0.92 to 0.95. Then the uniform kernel, meanwhile, is straightforward in design, but it has the excellent performance since it treats all intensity value uniform inside of the windows and exhibits much reduced sensitivity to local intensity variation, which yielded J-code from 0.70 to 0.75. The noise sensitive kernels include the uh, byweight Ipan Cherkov. The others kernels has the markedly worse performance for the Jacob value. This due to their distinctness and the absence of outlier and overlapping intensity distribution, which may distort the structure. Consequently, the conclusion is that the Gaussian and uniform can provide an optimal combination of segmentation, accuracy, resilience, and uh, processing economy. Uh, Conclusion.